Okay, let's just dive right in. Imagine a massive data set. I'm talking millions upon millions of numbers. You're tasked with finding the exact median value, or maybe the smallest, or even the 100th smallest item. But there's a massive catch here. Sorting the entire thing first is computationally impossible for your system. So, how do you find exactly what you're looking for without organizing the whole pile? Think about the contrast here. You have the brute force burden of organizing every single item versus the surgical precision of selection algorithms. I mean, if you just need the exact ith smallest element, forcing your computer to sort absolutely everything else around it is an incredible waste of time and energy. Our goal is to be highly targeted. We just want that one specific element and nothing else.
Selection algorithms. Welcome to this explainer, where we're going to trace the really brilliant evolution of these algorithms. We'll start from a naive randomized shortcut that programmers use and follow the math all the way up to a guaranteed masterstroke that secures the exact element you need with unbelievable efficiency.
Here is how we're going to break it down today. 1. The luxury of sorting. 2. Randomized Quick Select. 3. The partition step. 4. Deterministic selection, and finally, 5. The median of medians. Let's get right to it.
Part 1. The luxury of sorting. Pragmatic, sure, but incredibly costly.
Because here's the thing, sorting the entire list is a luxury we honestly just cannot afford. When we need to find a median, human instinct tells us to just order the list first so our target sits neatly at the right index. But if our elements haven't been ordered yet, it's virtually impossible to know if the element at index 0 is actually the true first smallest number. To know for sure, you traditionally pay a heavy computational tax to sort it all. And in modern computer science, when you're dealing with big data, that luxury is completely gone.
So, we need a clever hack, which brings us to Part 2, Randomized Quick Select.
This algorithm actually borrows heavily from the famous quicksort algorithm, but it has a special trick. It preserves the index of elements as it runs, without fully sorting the entire list. So how does this hack work? Well, we declare a split index right in the middle. We then compare that split directly to our target k, the specific element we're hunting for. If our split perfectly aligns with k, boom, we've instantly struck gold. We've found our element and the algorithm can stop right there.
But what if we don't hit the jackpot right away? Well, we look at the list we've physically divided. If our target T is greater than our split index, we know definitively that our target is somewhere on the right side. So we completely ignore the left side of the array. We just throw it out. We recursively search only the right side. By literally throwing away half the data at every single step, we're saving massive amounts of computational time.
Part 3. The partition step, the actual core engine of the algorithm.
Let's see how this physical dividing actually plays out. First, we select a random pivot, often just grabbing the very first element in the unordered array. Next, we partition the list around it. Basically, we shift all the elements smaller than our pivot to its left and all the larger elements to its right. Finally, as we just talked about, we recursively search the remaining half where we know our target actually lives.
But wait, there's a pretty massive flaw here. Picking the first element as a pivot, that's a totally random decision. What if our list is already mostly sorted in reverse, and we accidentally pick the absolute worst possible pivot? If we get unlucky with a bad split, we aren't throwing away half the data at all. Our energetic, fast algorithm suddenly plummets into a sluggish, worst-case performance of O of n squared. And when you're dealing with big data, O of n squared is an absolute disaster.
Enter Part 4, Deterministic Selection, guaranteeing O of n time.
This is our masterful resolution to that worst-case scenario. The goal here is simple but incredibly powerful. Remove the luck factor entirely from our pivot choice and mathematically guarantee a worst-case performance of O of n, no matter how messy the initial data is. Instead of just crossing our fingers and grabbing the first element, we deliberately walk through a mathematical sequence to force a genuinely good split every single time. We split the list into groups of 5, find their medians, recursively find the true median of those, and then partition around that reliable number.
And that specific approach brings us to Part 5, the median of medians, the ultimate safeguard.
Conceptually, this median of medians function is basically our ultimate safeguard. It does a little bit of pre-work up front to ensure we find an approximate true median. By doing this, we absolutely guarantee that when we finally do our partition, our array is sliced cleanly down the middle, avoiding that disastrous O(n) squared scenario entirely.
To make this super concrete, imagine taking an unordered list of 25 numbers.
We deliberately slice this big list up into tiny 5-element sublists. So group 1 has 5 numbers, group 2 has 5 numbers, all the way to group 5.
Then we go through each of those tiny groups and just pull out their individual medians. From our 25 original items, we've now extracted just 5 numbers: 15, 21, 60, 10, and 22. Just like that, we've given ourselves a brand new, much smaller list to work with.
Now, you might actually be laughing at the irony here. If you look at the real code for this, you'll see we actually use Python's built-in sorted method to find those tiny group medians. You're probably thinking, wait a minute, wasn't our entire goal to avoid sorting? Well, yes. But because we're strictly only ever sorting negligible maximum 5-item lists, the performance impact on the overall algorithm is practically zero. We are technically sorting, sure, but at a microscopic scale that doesn't hurt our speed at all.
By recursively applying this exact logic, finding the median of those group medians, we ultimately secure our true pivot. We now have a mathematically backed median sitting right in the middle, perfectly dividing all lower elements to its left and all greater elements to its right. We achieve a brilliant split, and we didn't have to rely on luck for even a second.
So I'm going to leave you with this thought to chew on as we wrap up this explainer today. If we can use algorithms like the median of medians to guarantee lightning-fast ON selection without fully sorting our massive datasets, how often in your own code are you paying the luxury tax of full sorting? Next time you reach for a blanket sort function, maybe ask yourself if a clever deterministic selection is really all you need. Thanks for joining me on this explainer, and keep exploring.